My name is Krystyne Kontos, and welcome to She Wants the Derivative, where we will engulf ourselves in a world of finding properties of derivatives and integrals of functions. I wish I were your derivative so I could lie tangent to your curves. So far in this course, you have expanded your knowledge in the rules of differentiating and derivatives. In all functions, the first and second derivative test aid you in analyzing important variables of a graph, rate of change, and whatnot. You and I both know that you're here because you've reached that point in time in calculus where you must tackle Chapter 5, Exponential Logarithmic Functions. In this particular lesson, we will be tackling derivatives of exponential functions and its applications. These derivatives can be used to solve problems involving growth in population or investment, important in statistics and manufacturing of goods in society. For this sort of application is located on page 274, number 6 in your textbook, where the infestation of fruit flies is investigated. Let's take a look. Before we begin, let's go back to some prior knowledge that we should know before tackling this kind of question. Number 1. An important derivative rule in exponential functions is the constant multiple rule. F at x equals the constant times a function, and f prime at x, the derivative, is equal to the constant times the prime of that function. Number 2. Euler's constant is the base for which the function and its derivative are identical. So, f at x equals f prime at x. The value of Euler's constant is between 2.71 and 2.72. This is the base of the exponential function to which a function and its derivative will be identical when plotted. 3. The natural logarithm is the logarithm to the base e of a number. Ln at x is equal to log base e at x, which can be used to understand the next points. 4. Ln x is the inverse of e to the x function. You can use it to solve for an exponent, which has a variable. You can use this concept to understand how ln a, both sides, essentially brings down the exponent to the plane, where the rest of the variables are. 5. The natural logarithm, ln, of a number is the apparent derivative of such number to an exponent variable x. This phenomena is derived through the Euler's constant e, whose natural logarithm is 1 when this occurs, in turn achieving its derivative of its base to be constant e to the x. So this is kind of related to our tip number 2. So we can sum this up saying f at x equals b to the x. Its derivative, f prime to the x, equals ln b times b to the x. 6. In exponentials, it is important to note that the derivative rate of change of an exponential function is also an exponential, but is simply a vertical stretched function to the relation of the original. So as we saw in point 5, that ln b would act as that vertical stretch. So we can model this as f at x equals b to the x. The derivative of that function is a, meaning the vertical stretch factor, times b to the x. Now let's get to the question. A fruit fly infestation is doubling every day. There are 10 flies when the infestation is first discovered. If you have ever left food out for too long, you can understand the infestation. So part A, write an equation that relates the number of flies to the time. First, let's break down the question to variables. Let us have n represent the number of fruit flies as a function of time, t in days. We know that n at t is the dependent variable, so it will be correlated with the y values of the function. We also know that the time is an independent variable, therefore is correlated with the x values of the function. This allows us to understand the relationship between base f at x and our new n at t. The n initial number of fruit flies is an important variable that will be surrounded by brackets. If we understand that the growth is doubling, we can understand that the function is multiplied by 2 to the exponent of the time variable of t. Therefore, the relationship of the growing population of the flies over time can be modeled n at t equals 10 times 2 to the power of t. So let's move on to part B. Determine the number of flies present after 1 week. This is quite simple. First, state your nodes. You must convert 1 week into 7 days as your formula permits time in a measurement of days. Plug in 7 into your equation, and you should achieve the answer of 1,280 flies. Therefore, after 1 week, 1,280 flies will be present. Now on to part C. How fast is the fly population increasing after 1 week? In this question, you should understand that it is asking for a rate as it mentions how fast the population is increasing after a time. To find how fast the flies are increasing at any time, differentiate the function with respect to time. This is where we will implement finding the derivative, then plug in the known variable of t equals 7. Using the blend of the constant rule and the knowledge of b to the x equals the natural logarithm of the base times the base to the x, we are able to differentiate. The base equals 2, so the derivative of the function is n prime t equals 10 times ln 2 times 2 to the power of t. Now that we have got our derivative, we can plug in our known value and get our answer of 887 flies. Remember, when writing this out, you must be mindful of putting the exponential last in order. Therefore, the population of the fruit flies is increasing 887 flies per day after 1 week. If graphed, this derivative function will be vertically stretched by a factor of ln 2. Now on to part D. How long will it take for the fly population to reach 500? We will be going back to our base function for this question. First, we will state our knowns, which is the value of n at t, which is equal to 500 flies. We need to solve when the value of t will correspond with n at t, so we will sub it into the equation. Divide the value of 10 on both sides. What you do to one side, you must do to the other, right? To reduce the left to 50. Now for the confusing part. We cannot divide a number with an exponential variable to solve. We must take the natural logarithm, ln, of both sides to essentially bring down the t variable. Now you will divide in ln 50 by ln 2 to achieve your value of t, that is 5.64. Now we must further interpolate this data. Therefore, the population of fruit flies will be at 500 a little after 5.5 days. Now for the final part. Part E. How fast is the fly population increasing at this point? This solution is proceeded in the same fashion as part C. To find how fast the flies are increasing at any time, differentiate the function with respect to time. Use the derivative function found in part C and plug in your known value. We will first state our knowns from part D of t equals 5.64 days. We will not round off our previous answer to achieve a more accurate result. You will get an answer rounded to 346. Therefore, we can conclude the fly population is increasing 346 fruit flies per day after over 5.5 days. As an added bonus, we will graph our derivative and interpolate our results. It's shown that the fruit fly population's growth seems to increase greatly of 546 flies a day after 1 week in comparison to the 5 days and a half. That's 2 days and a half. This just goes to show how important calculus is in observing trends and situations. We can infer that there might be something in the area that is causing this rapid increase of it could be farmed for a strange reason. Corners can discover how long a body has been rotting there by seeing how many fruit flies there are. You can even interpolate through the duration of time the population of flies that may be resting in your locker after leaving cantaloupe in there over the break.
Why? Isn't it amazing that all of life is monitored through the simple concepts of calculus? Anyways, that's all, folks. Be sure to check out my other videos. And remember, alcohol and calculus don't mix. So never, I mean never, drink and derive. Sponsored by Mathematicians Against Drunk Deriving.